I'm Quinlan, and I'm going to be talking on behalf of my team about smart textiles, more specifically about replacing steel fibers in smart textiles to improve sustainability. So in this video, we'll be going over the background and motivation of our project, how we define the problem, the design process, our technical analysis, and finally the takeaways from this presentation. The topic today is the notion of smart textiles. They are defined as textiles that can sense and react via an active control mechanism to environmental conditions or stimuli from mechanical, thermal, chemical, electrical, or magnetic sources. Typically, smart textiles are made through various fabrication methods. 1. Assembling textile fibers that have additional functions. 2. Attachment of commercial off-the-shelf components. Or 3. Hybrid approaches combining both commercial and textile functionalities. According to a report by Grandview Research Inc., it is expected that by 2025, the global smart textile market size will reach $5.55 billion USD. It is anticipated to witness substantial growth due to the increasing product demand from several applications such as, but not limited to, sports and fitness. An increasingly popular application of smart textiles is wearable technology. The vision for wearable technology is that it will be integrated into the daily lives of users, as it would be able to automatically recognize the activity and behavioral statuses of users, as well as their surrounding environment. This allows the technology to use the information collected to adjust the system's configuration and functionality. So now let's go over our defined problem. Currently, the most common conductive metal found in smart textiles is steel, as it is conductive and durable but can also be made soft and flexible. However, steel is a non-renewable material, and it acts as a contaminant when attempting to recycle the textile. Even with the increasing growth in the smart textiles industry, it has its limitations. Currently, smart textiles are woven with stainless steel yarn, silver threads, or other precious materials. However, valuable materials contained in e-textiles are dispersed within textile bulk materials, which makes e-textiles a low-grade feedstock for metal recycling. Fiber recycling, in turn, is seriously compromised by e-waste contaminating the textile materials. Despite its increasing popularity, very little attention has been paid to how smart textiles will be managed at the end of their life. To summarize, the problem addressed in this project was that the conductive components of smart textiles are incompatible with current textile recycling processes, making the recycling of smart textiles challenging and expensive overall. The team is proposing the replacement of the usually steel fibers with a nanocellulose-based biopolymeric fiber, dip-coated with a conductive layer of metal powders, carbon nanoparticles, or conductive polymers. This will reduce the environmental costs of the manufacturing process and will result in increased sustainability in fabricating the product, as the energy costs will be lowered. This next session will detail the design process and our proposed design solution. This slide illustrates the integration of conductive fibers with the base fibers in smart textiles. The cellulose-based fibers will be coated with metal powders, carbon nanoparticles, or conductive polymers through dip coating for conductivity. These nanocellulose fibers, CNF, can be made from waste material, thus reducing the waste that ends up in landfills. Currently, the conductive fiber used in smart textiles are usually made of stainless steel, copper, or other materials. The most common method used for fabrication of the metal fibers is bundle drawing, as seen on the left. Since the proposed solution is the integration of nanocellulose fibers, which will just replace the metallic fibers, its implementation has little effect on the weaving and knitting process during the manufacturing of smart textiles. Therefore, the focus of the design process and analysis will be on the manufacturing processes of the fibers themselves. Nanocellulose is created from cellulose, which can be extracted from sources such as, but not limited to, wood, cotton, hemp, flax, and wheat straw. CNFs are therefore biodegradable and renewable materials, making them highly sustainable. The creation of continuous fibers from CNFs to be used in smart textiles entails two different processes. 1. Creation of the fibers, and 2. Coating of the fibers with conductive material. The process of converting nanocellulose into continuous fibers is usually done through a spinning process, which includes solution-free methods such as melt spinning, and solution methods such as dry spinning, wet spinning, and electrospinning. The left figure shows a simplified version of the four processes involved. The team considered economic factors such as throughput, cost of equipment, as well as the properties of the material required for the application. The table on the right shows a comparison of the characteristics for each fabrication method. High tensile strength was not deemed a strong requirement for application in textiles. Moreover, the team believes that for the solution to be feasible, there needs to be a high throughput and a small barrier to entry, which would incentivize companies to make the switch to the more sustainable material. Therefore, melt spinning was considered the best and most feasible method for fiber fabrication due to the low initial cost, high throughput, and simple application. It also enables a shorter lead time, thus making it an attractive fabrication method for companies. Since nanocellulose has poor conductive properties, the fibers must be coated with a conductive coating with materials such as conducting polymer composites, metals, or carbon-based materials, such as carbon nanotubes, carbon nanopowders, and graphene. Some of the methods used for coating the fibers include dip coating and vapor deposition. Even though vapor deposition ensures a uniform coating, whereas dip coating does not, it requires high temperatures and is unsuitable for organic compounds. Hence, despite its limitations, the team is proposing dip coating as the preferred method for coating the fibers due to its simplicity and compatibility with a wide range of substrate solutions. A simple illustration of the dip coating is shown on the slide. A flowchart showing the proposed solution and the associated manufacturing process is shown. 1. Melt spinning to manufacture the continuous nanocellulose fibers. 2. Dip coating into a conductive coating to produce conductive continuous nanocellulose fibers. Then the current process of fabrication of metal fibers through bundle drawing. Then the conductive continuous nanocellulose fibers and metal fibers are woven and knitted, resulting in a wearable technology product. Now we'll dive into the technical analysis and some of the takeaways from this project. The table shown summarizes the quantitative improvements from the proposed solution when compared to the current methods. The use of nanocellulose to replace the metals in smart textiles have numerous benefits. Stainless steel and copper yarns are the most commonly used metals in the production of smart textiles. This means that when looking at the best case scenario, the use of CNF has the most environmentally friendly production costs. Moreover, smart textiles are often exposed to tensile stress, which can lead to fracture of the interwoven conducting yarns. The use of CNF would result in increased durability of the smart textile and reduced weight, which would increase the comfort for the user. When used in sizable quantities, CNF could provide insulating characteristics to the wearable technology due to its low thermal conductivity. Moreover, CNFs have good mechanical compressibility and fragility resistance. However, despite the environmental benefits and superior mechanical properties, the cost of raw materials for the CNF is more costly than for stainless steel. As cost is one of the biggest driving factors in the decision-making process in businesses, this is one of the biggest barriers to the implementation of CNFs. When looking at disposal, recycling old e-textiles will be difficult because valuable materials are dispersed in large amounts of heterogeneous textile waste. Moreover, the electronic components can act as contaminants in the recycling of textile materials. Therefore, if the textile itself is also made of biodegradable fibers, the integration of CNF means that the product could still be decomposed. Moreover, this would also provide easier recycling of the smart textile as it reduces the chances of contamination during recycling and downcycling. However, CNFs also have higher water absorptivity, which leads to swelling and a degradation in mechanical properties. Due to the electrical nature of wearable technology and the high absorption of fabric, the team is predicting that water absorption will not be a major issue. Another potential downfall in the integration of CNF into smart textiles is due to the additional manufacturing process in conductive nanocellulose fiber manufacturing. However, due to the simplicity and low initial costs related to the processes, the barrier to implement the proposed solution is quite low given the verification of the validity and the success of the proposed methods. In conclusion, more work can be done in looking to the feasibility of continuous fiber manufacturing. We would need to test the fabrication of nanocellulose using melt spinning to determine its mechanical properties, especially the temperature range required for extrusion so that no thermal degradation takes place. In addition, testing for coating materials of the organic material needs to take place to maximize factors like conductivity and bond strength as well as minimize costs. Cost will likely be the driver for much of the gravity of this idea. Thus, sufficient testing should take place to minimize costs of production in general before the use of nanocellulose fibers becomes a viable and marketable option for textile producers. Other ways to minimize costs include integrating manufacturing of nanocellulose with other polymers to make use of current manufacturing processes instead of creating brand new ones. Integration is no easy feat, but work can be done to look into this. Overall, the use of nanocellulose fibers in textile fibers themselves have massive ramifications for recyclability and sustainability of materials. If more work can be done in reducing costs of production and cost of materials, the future of smart textiles looks bright indeed. Thank you for listening. We hope you enjoyed this video on smart textiles, on replacing fibers in smart textiles to improve sustainability.